Hello everyone, myself Prabhas Singh, Assistant Professor from ABES Engineering College, Ghaziabad. In this lecture, we will discuss about the other two problems of backtracking, that is graph coloring, and another is Hamiltonian circuit problem. In the last lecture, we have discussed about the what is backtracking and the n-queen problem and a subset sum problem. So moving ahead, what exactly is backtracking? Backtracking is a systematic approach of trying out all possible solutions until we find the one that works. Here we talk about the graph coloring problem. We are given a graph. We are asked to color all the vertices with M colors in such a way that no two adjacent vertices will have the same color. That is, we are given this graph. We initially have, let's start with our vertex A. We given it a green color. Now we have this as an adjacent vertex and this as an adjacent vertex. We can traverse anyone. First, let's consider this. When we reach this vertex, it is defined that the color of this vertex will never be green. So we introduced another color named as blue. Then we come at this vertex. This vertex adjacent to this vertex is this. So it was defined as the color of this vertex is green. Now this is green. We reached B where we get this as green and this as green. So we introduce another color here as blue. So in a given graph where we were given four vertices and the four edges, we decode that there will be the two colors that will be used to color a graph in such a way that the no adjacent vertex will have the same color. We have to ensure that the colors to the graph will be used as minimum. Because if we talk about this graph, we can simply give four colors. So hence we have to maintain that we are given a graph. We have to color the vertices in such a way that the no two adjacent vertex will have the same color and it should use the minimum number of colors. That is M coloring problem. Given an undirected graph and number M, if a graph can be colored with at most M colors so that the no two adjacent vertices are colored with the same color, and the coloring means the assignment of the colors to the vertices. What the naive approach is, we first find all the permutations of the color possible to color every vertex of the graph using a brute force approach. Clearly, it will be taking more time. In backtracking approach, makes the process to solve the problem more efficient by avoiding the bad decisions. Because if we color it green, then we do not have to explore another vertex as green. This is a bad choice. We eliminate these things using a backtracking need to made in a naive approach. Hence, the step-by-step approaches, we start by coloring a single vertex, then move it to adjacent vertex. We color it with a color which have not been used to color any of the connected vertex. After coloring, it will be moved to adjacent vertex which is uncolored. We repeat the process until all the vertices of the graph are colored. We will see this with the help of an state space search tree. What will happen is, initially we started with a root node. We color it as green. There are the two possibilities, green and a blue. Green will not be possible because adjacent vertex will have the same color and the blue is possible. Once we color it as blue, where are another we have two possibilities, that is blue and green. Here blue is not possible and green will be possible. So we will get a path as this, and this. This is one of the solution. And for the, we will have another path as this is what? Green, blue, green, blue. Here we can have a solution as blue, green and blue, green. That is simple where blue, green, then blue, then green. These are the two possible solutions for a given graph. We can think of another graph here. Let's take an example A. We are given a vertex B, then we are given a vertex C, then we are given a vertex D here. Then we are giving a vertex E, then F. Let's take an example. This is a graph. Now, what will happen is we will simply give red color to this node. Now, adjacent to this are this and this. We start exploring from here. And it is defined that we will not give a red color. Let's introduce a green color here. Then we go to this vertex. Then we will see that the green color will not be assigned. Then we will use a previous color as red. Then we come to this vertex. Then we can simply give a green color here. Now here we reached. Adjacent to this are this and this. We give another color it as blue. Then again we reach here. What will happen is this vertex we have adjacency as this, adjacency as this, and adjacency as this. That is blue, green, and red. This gives emergence to a new color. But can we backtrack in order to find or solve this problem with a minimum number of colors? That is, what we will do is, when we are giving is this blue color, we are seeing adjacent as red and green. Can we have the two vertices that are adjacent must have a same color? Then what we will do is, we can simply give this blue. If we give this blue, then this color can be given as green. Now, what we get here? We have this vertices as green. We have this vertex adjacent as green. And we have this vertex adjacent as red. So, we give exposure to blue. That blue can be possible here. Hence, we backtrack in such a way in order to make this green to blue and this blue to green so that we can have two adjacent vertex along F that will be having a same color as green. This will help us to solve this problem with the three colors. This is a graph coloring problem. Now, if we talk about the Hamiltonian circuit problem, here we are given a graph where vertices and edges are given. We have to find a Hamiltonian circuit using a backtracking approach. So what we will do, we start our search from any arbitrary vertex, that is A, and simply build an implicit tree or the state space search tree for the next. Next adjacent vertex is selected on the basis of the alphabetical order. If at any stage any arbitrary vertex makes a cycle, then any other vertex A, then we have to say that dead end is reached. What is a Hamiltonian circuit problem is, we start from any arbitrary vertex A, then we explore the vertices in the alphabetical order B, C, D. Let's suppose these are the adjacent. Then we see which is adjacent to B. Then we keep on exploring the vertices on the basis of DFS approach and think from starting from A, covering all the vertex and then coming back to A is a Hamiltonian circuit. The circuit must be formed after reaching all the vertices. Agreed? Now, if we talk about this example, here, this is a graph given to us. What we have done is we started initially with a vertex A. Once we started initially with a vertex A, we simply see what are the adjacent vertex to A that are B, C, and D in a given graph. That is this, and this. After seeing an adjacent vertex, we simply keep on exploring B. If we see B, we have seen the adjacent to B are C and E in our graph. Then we see C, then we see the adjacent to C are D and E. We keep on exploring the leftmost vertex because we are following our DFS. As in backtracking, we must follow a depth first approach. In D, we will see E and F. Then after seeing E, we will get F because here we get a dead end because we are not able to reach A from this. Hence, we backtrack to E. E have all the possibilities as this, hence we backtrack to D. Once backtracking to D, we get a dead end here. From D, we get F. Here, then again that dead end. And then E. So we simply backtrack again to C. So what we are getting is we get dead end at D, we get dead end at E, we get dead end at F. Now we keep on backtracking, we get at C. Here C, we get E. Adjacent to E are F and D. Then we explore F. F adjacent to F are D and E. Then we explore D, and adjacent to D are A. So what happen is we get a cycle or Hamiltonian circuit as this. That is A, B, C, E, F, D, A. Hence, this is one of the solution for the given problem. In this, what we have to do, we have to start from any of the node that we will consider as a root. Then we keep on exploring the adjacent node, and we have to pick the node that appears first in the alphabetical order or lexicographical order, right, or the numerical order. And we keep on exploring as an DFS approach until we find a solution that works. Here we have seen that how we backtrack from F, then backtrack from E, then backtrack from D, and we get a solution from C. Here we have represented what we are doing, how we backtrack for each and a step, and this is a solution which we have achieved.